Hey everyone, tonight we're going to dive into something that's been quietly troubling astronomers for the past few years. Stars that simply vanish, not in the dramatic way you might imagine with supernovas or black hole encounters, but in a much more mysterious fashion. One moment they're there in our telescopes, steady and reliable as they've been for decades or even centuries of observation, and then nothing. Just empty space where starlight used to be. It's the kind of phenomenon that makes you pause and wonder what we're really looking at when we gaze up at the night sky. We tend to think of stars as permanent fixtures, cosmic lighthouses that have been burning since long before humanity took its first steps. And for the most part, that's true. Stars live for millions or billions of years, following predictable patterns of birth, life, and death that we've mapped out pretty well. But these disappearing stars don't fit the pattern. The whole thing started when astronomers began comparing old photographic plates from the 1950s and 60s with modern digital sky surveys. It was routine work, really, the kind of careful, methodical comparison that science depends on. But what they found was anything but routine. Hundreds of stars that appeared in the older images were simply gone in the new ones, not dimmed, not shifted position, not hidden behind dust clouds. Gone. Now, before we go any further, let's sit with that for a moment. We're talking about objects so massive and energetic that their light travels across decades or centuries of space to reach us. These aren't distant galaxies that might flicker in and out of visibility as gravitational lensing bends their light around massive objects. These are individual stars in our own cosmic neighborhood, relatively speaking, and they're vanishing without a trace. What makes this even more intriguing is the timeline. These disappearances aren't happening over the geological timescales we usually associate with stellar evolution. We're talking about changes that occur within a human lifetime, sometimes within just a few years. That's practically instantaneous in cosmic terms, like a candle being snuffed out in a cathedral. Some of these missing stars were red giants, the swollen, aging suns that should have been visible for millions of years yet to come. Others were main sequence stars like our own sun, supposedly in the prime of their stellar lives. A few were even massive blue giants that should have eventually gone out in spectacular supernova explosions, events so bright they can outshine entire galaxies for weeks. But here's where it gets really interesting. There's no debris field, no expanding shell of gas and dust, no neutron star or black hole left behind to mark their passing. It's as if these stars were simply edited out of the universe, removed so cleanly that even their final moments left no signature for us to detect. The phenomenon has a name now. The Vanishing and Appearing Sources During a Century of Observations Project, or VASCO for short. It's being led by researchers who are methodically cataloging these cosmic disappearances, building databases of stars that should be there but aren't, and the more they look, the more they find. This isn't just about astronomy or astrophysics, though those are certainly part of it. It's about the fundamental question of what we can really know about the universe around us. If stars can simply vanish without explanation, what does that say about the nature of reality itself? What does it mean for our understanding of cosmic processes that we thought were well established? Tonight we're going to explore these questions together. Not to find definitive answers, because honestly we don't have them yet, but to sit with the mystery and see what it might teach us about our place in a universe that's clearly more enigmatic than we ever imagined. To really appreciate what these vanishing stars might mean, we need to step back and think about humanity's relationship with the night sky. For most of our species' existence, the stars were the ultimate symbol of permanence and predictability. Ancient civilizations built their calendars, their navigation systems, and their mythologies around the assumption that the stars would always be there, following the same paths they'd traced for countless generations before. The ancient Egyptians called the stars the imperishable ones, and they built their entire conception of the afterlife around this idea of stellar permanence. The pharaohs weren't just buried with earthly treasures. They were oriented toward specific star patterns that would guide their souls through an eternal cosmic journey. The precision of their astronomical knowledge is still breathtaking today. The Great Pyramid of Giza aligns with Orion's belt with an accuracy that rivals modern engineering, and it was built over 4,000 years ago. But it wasn't just the Egyptians who saw the stars as eternal. The Greeks developed complex philosophical frameworks around the idea of celestial perfection. Aristotle taught that the heavens were made of a fifth element, fundamentally different from the earthly materials we know: unchanging, incorruptible, divine. This wasn't just scientific theory, it was theology. The stars were literally the realm of the gods, and their permanence was proof of divine order in the universe. Even when Copernicus shattered our geocentric worldview in the 16th century, the stars themselves remained untouchable. They were still the fixed backdrop against which planets wandered. That's what planet means, after all: wanderer. The stellar sphere was still perfect, still eternal, even if we were no longer at the center of it all. It took until the 20th century for us to really understand what stars are: massive nuclear furnaces fusing hydrogen into helium, burning through their fuel over billions of years in a process so steady and predictable that we can use it to measure cosmic distances and ages. We learned that stars do die, but slowly, following well-understood patterns. Small stars fade to white dwarfs over trillions of years. Massive stars explode as supernovas, seeding space with heavy elements that eventually form planets and, ultimately, life itself. This understanding gave us a new kind of cosmic permanence. Sure, individual stars might die, but they did so according to physical laws that we could map and predict. We could look at a star and know, with remarkable precision, how long it had been burning and how much longer it would continue to shine. The universe became clockwork, vast, ancient clockwork, but clockwork nonetheless. And then came the deep sky surveys, the systematic photography and cataloguing of millions of stars across decades of observation. This is where human patience and cosmic time finally intersected in a meaningful way. For the first time in history, we had photographic records spanning long enough periods to catch the universe in the act of changing. We expected to see supernovas, variable stars brightening and dimming in regular patterns, maybe the occasional stellar collision or black hole merger. What we didn't expect was to find stars that simply switched off like light bulbs. The thing is, our entire understanding of stellar evolution is built on the assumption that massive objects can't just disappear. Matter and energy are conserved. Einstein taught us that much. A star might transform its mass into energy through fusion, or collapse into a black hole, or blow itself apart in a supernova, but it can't simply cease to exist. The physics doesn't allow for it, unless, of course, our physics is incomplete. This is where the story gets really interesting, because the vanishing stars aren't just challenging our understanding of stellar evolution, they're challenging some of the most fundamental assumptions we make about reality itself. Conservation of mass and energy isn't just a scientific principle, it's one of the bedrock assumptions that makes scientific inquiry possible in the first place. When ancient peoples looked up at the stars and saw permanence, they weren't wrong exactly. They were seeing patterns that had held true for thousands of human generations. The North Star really was a reliable guide for navigation. The seasonal movements of constellations really did mark the passage of time with extraordinary precision. but they were seeing a snapshot, a moment in cosmic time that felt eternal because human lives are so brief in comparison. Now we're in a different position. We have telescopes that can peer billions of years into the past, instruments sensitive enough to detect the faintest whisper of radio waves from the edge of the observable universe. We can measure the cosmic microwave background radiation, the afterglow of the Big Bang itself. We've mapped dark matter and dark energy, those mysterious components that make up 95% of everything that exists. And yet, stars in our own galactic neighborhood are vanishing without explanation, reminding us that for all our sophisticated understanding of cosmic processes, the universe still holds secrets we haven't even begun to fathom. The evidence for vanishing stars comes from one of the most methodical and unglamorous types of astronomical research you can imagine, the painstaking comparison of photographic plates and digital sky surveys taken decades apart. It's the kind of work that requires extraordinary patience and attention to detail, qualities that aren't often celebrated in our age of spectacular space imagery and gravitational wave discoveries. But sometimes it's exactly this kind of careful, systematic observation that reveals the most profound mysteries. The story really begins with the Palomar Observatory Sky Survey, a massive photographic mapping project that captured images of the entire northern sky between 1949 and 1957. These weren't casual snapshots, they were precisely calibrated, methodically taken photographs that recorded the positions and brightness of millions of stars with remarkable accuracy. For decades, these glass plates served as the definitive record of what the northern sky looked like in the mid-20th century. Fast forward to the 21st century, and we have digital sky surveys of unprecedented scope and precision. The Sloan Digital Sky Survey, the 2-micron All-Sky Survey, the Gaia mission. These modern projects can detect and catalogue stars that are thousands of times fainter than anything visible to the naked eye. They can measure stellar positions with precision that would have seemed magical to earlier generations of astronomers. When researchers began systematically comparing these modern surveys with the old photographic plates, they expected to find exactly what you'd predict from a well-understood universe. Some stars would have brightened or dimmed slightly. A few might have moved perceptibly across the sky. Proper motion, astronomers call it. There might be the occasional supernova, the rare stellar merger, perhaps a few cases where improved instrumentation revealed that what looked like a single star was actually a binary system. What they found instead were stars that had simply vanished. The first few cases were easy to dismiss. Photographic plates can have flaws, modern surveys can miss faint objects, and there are plenty of legitimate reasons why a star might appear in one dataset but not another. But as the catalogues grew more complete and the comparisons more systematic, a pattern emerged that couldn't be explained away by observational errors or instrumental limitations. The VASCO project, led by researchers at the Nordic Institute for Theoretical Physics and other institutions, has now identified over 800 cases of objects that appear in mid-20th century surveys, but are completely absent from modern observations. These aren't marginal detections or questionable candidates. These are objects that showed up clearly on multiple photographic plates, in some cases over periods of years or decades, and then simply disappeared. What makes this even more compelling is the diversity of the vanishing objects. Some were red giants, stars in the final phases of their evolution that should have been visible for millions of years yet to come. Others were main sequence stars like our own Sun, supposedly in the stable middle period of their stellar lives. A few were massive blue giants, the kind of stars that burn hot and bright and should eventually go out in spectacular supernova explosions visible across vast distances. But here's the crucial detail. In none of these cases is there any sign of the debris that should be left behind by conventional stellar death. When a star goes supernova, it leaves behind an expanding shell of hot gas that glows brightly in radio waves and X-rays for thousands of years. When a star collapses into a black hole, it should leave behind gravitational signatures that we can detect with modern instruments. When stars merge or are disrupted by tidal forces, they create distinctive patterns in the surrounding interstellar medium. The vanishing stars show none of these signatures. It's as if they were carefully removed from the universe, extracted so cleanly that even their gravitational influence simply ceased to exist. Some of the most intriguing cases involve stars that were observed to fade gradually over periods of months or years before disappearing completely. This rules out simple observational errors or catalogue mismatches. These objects were definitely there, definitely visible, and then definitely gone. The fading patterns don't match any known type of stellar variability or evolutionary process. One particularly compelling case involves a red giant star in the constellation Lynx that appeared on every photographic survey between 1950 and 1997, maintaining consistent brightness and color. Modern surveys show nothing at that position. Not a faint remnant, not a white dwarf cooling in place, not even a diffuse nebula marking where the star used to be. Just empty space with the same background star field that was visible around the original star. The researchers have been careful to rule out more conventional explanations. They've checked for proper motion, the possibility that stars might have moved far enough across the sky to account for the apparent disappearance. They've looked for evidence of obscuring dust clouds or gravitational micro-lensing events that might temporarily hide distant stars. They've cross-referenced their findings with catalogues of known variable stars, supernovae, and other transient phenomena. In case after case, the conventional explanations fall short. These stars didn't move, didn't explode, didn't fade into white dwarf remnants, and didn't get obscured by intervening matter. They just switched off, leaving behind a mystery that challenges our most basic assumptions about how the universe works. When you start looking closely at these vanishing stars, certain patterns emerge that make the mystery even deeper. It's not just that stars are disappearing, it's how they're disappearing, and more importantly, what kinds of stars seem to be affected. One of the most puzzling aspects is the timescale. In conventional astrophysics, significant changes to stars happen over millions or billions of years. Even the most dramatic stellar events, supernova, neutron star collisions, black hole formations, play out over timescales that are long by human standards but brief by cosmic ones. A supernova might brighten over the course of weeks and then fade over months or years. A star collapsing into a black hole might take hours or days. But these vanishing stars are operating on a completely different schedule. Some disappear gradually over periods of years or decades, still fast by astronomical standards, but slow enough that we can actually watch the process happen. Others seem to switch off between one observation and the next, sometimes with gaps of just a few years between the last confirmed sighting and the first survey that shows them missing. There's also the question of stellar type. You might expect that if stars are disappearing due to some unknown but natural process, it would affect certain kinds of stars more than others. Maybe massive stars that are already unstable would be more susceptible. Maybe old, dying stars would be the primary candidates. But the vanishing stars don't follow those patterns. The sample includes main sequence stars that should be stable for billions of years, red giants that are following predictable evolutionary paths, and even some young hot stars that have barely begun their stellar lives. There's no obvious connection in terms of mass, age, composition, or evolutionary state. It's as if the disappearance mechanism doesn't care about conventional stellar physics. Perhaps even stranger is the distribution across the sky. If the vanishing stars were caused by some kind of local phenomenon, a nearby black hole, a dark matter concentration, or some other gravitational anomaly, you'd expect them to cluster in particular regions of the sky, but they don't. They're scattered across the celestial sphere with no apparent pattern, suggesting that whatever is causing them operates on a much larger scale than anything we typically consider in stellar astrophysics. Some cases show particularly unusual behavior in the months or years leading up to the disappearance. A few stars exhibited irregular brightness variations unlike any known type of stellar variability. Others showed subtle color changes that don't match the spectral evolution patterns we see in conventional stellar aging. One red giant in the constellation Cygnus actually appeared to brighten slightly before vanishing, the opposite of what you'd expect if it were simply dying or being obscured. There are also intriguing correlations that might or might not be significant. Several of the vanishing stars were part of binary systems, but their companion stars remain visible and apparently unaffected. This rules out large-scale gravitational disturbances that would affect entire stellar systems. Whatever removed the primary star did so with surgical precision, leaving the orbital companion to continue on its path as if nothing had happened. A few of the disappeared stars had been subjects of detailed spectroscopic studies in the years before they vanished. Their spectra showed normal stellar atmospheres with typical abundances of hydrogen, helium, and heavier elements. There were no unusual spectral lines, no signs of exotic matter or extreme physical conditions. Right up until they disappeared, these stars looked like perfectly ordinary members of our galaxy's stellar population. This raises profound questions about the nature of observation itself. If these stars were behaving normally in every measurable way right up until they vanished, what does that tell us about the limits of our ability to understand stellar physics? Are there processes occurring inside stars that we simply can't detect with current instruments? Are there forms of matter or energy that can dramatically alter stellar evolution without leaving any spectroscopic signature? The most unsettling possibility is that the vanishing stars are exactly what they appear to be, proof that our understanding of stellar physics is fundamentally incomplete. We've built elaborate theoretical frameworks to explain how stars work, based on what we can observe and measure. But if stars can simply cease to exist without following any of the pathways our theories predict, then we're clearly missing something crucial about the nature of stellar matter and energy. The anomalies don't just challenge specific theories about stellar evolution. They challenge the assumption that the universe operates according to consistent, discoverable physical laws. When faced with phenomena that don't fit conventional physics, scientists and theorists inevitably begin to explore more speculative possibilities. The vanishing stars have prompted exactly this kind of creative thinking, leading to theories that range from exotic astrophysics to considerations that push the boundaries of what we normally consider scientific inquiry. One of the more mainstream explanations involves the concept of primordial black holes, theoretical objects that might have formed in the very early universe shortly after the Big Bang. Unlike the stellar mass black holes we're familiar with, which form when massive stars collapse, primordial black holes could have a wide range of masses, including some small enough to pass through stellar systems without immediately revealing their presence. If such an object passed close enough to a star, it could potentially disrupt the star's internal structure in ways that might cause rapid collapse or even complete absorption, leaving little or no detectable trace. But this explanation has problems. Primordial black holes of the right size should be extremely rare, and their gravitational effects should be detectable in other ways. The statistical distribution of vanishing stars doesn't match what we'd expect from random encounters with wandering black holes. And even if a star were completely absorbed by a black hole, the process should generate enormous amounts of X-ray and gamma-ray radiation as matter spirals in, radiation that modern telescopes should easily detect. More exotic theories involve concepts from advanced theoretical physics. Some researchers have suggested that the vanishing stars might be evidence of phase transitions in stellar matter, sudden changes in the fundamental nature of the material making up the star. Just as water can suddenly freeze into ice under the right conditions, stellar matter might undergo transitions into forms we don't yet understand, forms that might not radiate electromagnetic energy in ways we can detect. This connects to broader questions about dark matter and dark energy, those mysterious components that make up most of the universe but barely interact with ordinary matter. Could some stars be transforming into dark matter configurations? Could they be moving into dimensions or states of existence that place them beyond our ability to observe, even though they continue to exist in some form? Then there are the theories that really push the boundaries of conventional thinking. The vanishing stars have inevitably attracted attention from researchers interested in the possibility of advanced extraterrestrial civilizations. If a sufficiently advanced civilization wanted to harvest the energy of entire stars, perhaps by constructing massive engineering projects around them, the process might appear to us as stars simply disappearing. This isn't as far-fetched as it might sound. Astronomers have seriously considered the possibility of detecting so-called Dyson spheres, hypothetical megastructures that could completely surround a star to capture all of its energy output. A civilization capable of such engineering might be able to make stars effectively invisible to distant observers while still utilizing their energy for purposes we can barely imagine. Freeman Dyson himself, the physicist who first proposed this concept, suggested that advanced civilizations would inevitably face energy limitations that would drive them to undertake stellar-scale engineering projects. The vanishing stars could represent this process in action, not the construction of Dyson spheres necessarily, but some form of stellar engineering that removes stars from our observable universe. More speculatively, some theorists have connected the vanishing stars to ideas about the nature of reality itself. If our universe is some kind of simulation, as some physicists and philosophers have seriously proposed, then the disappearing stars might represent computational resources being reallocated or updates to the underlying program. Objects that are no longer needed for the simulation's purposes might simply be removed to free up processing power for other calculations. This simulation hypothesis isn't just science fiction speculation. It's been seriously considered by respected physicists and computer scientists. If advanced civilizations inevitably develop the ability to create detailed simulations of their own universes, then simulated realities might vastly outnumber real ones, making it statistically likely that we're living in a simulation ourselves. From this perspective, the vanishing stars might be glitches in the system, or evidence that we're approaching the computational limits of whatever process is generating our experienced reality. It's a deeply unsettling possibility, but one that some researchers argue we should take seriously given the rapid advancement of our own simulation and computing capabilities. What's striking about all these theories is that they force us to consider possibilities that extend far beyond conventional astrophysics, into realms of exotic physics, advanced technology, and fundamental questions about the nature of existence itself. Of course, before we venture too far into exotic theories about stellar engineering or simulated realities, it's worth considering more conventional explanations for the vanishing stars. Science has a long history of mysterious phenomena that eventually yielded to more mundane explanations, and the principle of Occam's razor suggests we should exhaust simpler possibilities before embracing more speculative ones. The most straightforward explanation is observational error. Comparing astronomical observations across decades or centuries is fraught with potential pitfalls. Photographic plates can degrade over time, developing flaws or losing sensitivity in ways that might make faint stars appear to vanish. Different telescopes have different capabilities, and what appears as a clear stellar detection on an older, less sensitive instrument might fall below the detection threshold of a modern survey if the star has dimmed slightly over time. The Vasco researchers have been careful to address these concerns, cross-referencing their findings with multiple independent observations and using statistical methods to weed out likely false positives. But the possibility of systematic errors remains, particularly when dealing with objects at the limits of detectability. Even small changes in stellar brightness, atmospheric conditions, or instrumental calibration could potentially account for some of the apparent disappearances. Another conventional explanation involves interstellar extinction, the dimming of starlight by dust and gas in the space between stars. Our galaxy is far from empty. It contains vast clouds of microscopic particles that can absorb and scatter light, making distant stars appear fainter or even completely invisible from our perspective. If a dense cloud of interstellar material drifted between Earth and one of these stars over the past few decades, it could explain why the star appears to have vanished. This explanation works particularly well for some of the more distant stars in the VASCO catalogue. Interstellar dust clouds are known to move and evolve over timescales of decades or centuries, and their effects on stellar visibility can be dramatic. The challenge is that dust extinction typically affects all wavelengths of light, but not equally. It tends to make stars appear redder as blue light is preferentially absorbed. Most of the vanishing stars don't show this characteristic reddening in their final observations before disappearing. There's also the possibility of gravitational microlensing events that work in reverse. When a massive object passes between Earth and a distant star, its gravity can act like a lens, actually making the background star appear brighter than it normally would. If such a lensing event were ending during the period between the old and new surveys, a star might appear to vanish simply because it's returning to its normal, much fainter brightness, potentially below our detection threshold. This explanation requires some fairly precise timing and alignment, but it's not impossible. The Milky Way contains billions of stars, brown dwarfs, and other massive objects that could potentially serve as gravitational lenses. The statistical likelihood of such events affecting hundreds of stars in the Vasco sample is low, but not zero. More intriguingly, some of the vanishing stars might be examples of extremely rare types of stellar evolution that we simply haven't observed before. Our understanding of stellar physics is based on observations of relatively common stellar types and processes, but the universe is vast, and statistical inevitability suggests that there should be stellar events so rare that we've never had the chance to study them directly. Consider that we've only been doing systematic astronomy for a few centuries and precise photometric observations for less than a century. That's an incredibly brief moment in cosmic time. It's entirely possible that there are stellar processes that occur on timescales of decades or centuries, fast by astronomical standards, but too slow for us to have caught them in action before now. Some stars might undergo internal changes that cause them to suddenly collapse without the explosive violence of a supernova. Others might transition into exotic states of matter that don't radiate in the electromagnetic spectrum. Still others might be affected by interactions with dark matter concentrations or other phenomena that we're only beginning to understand. There's also the human factor to consider. Pattern recognition is one of our species' greatest strengths, but it can sometimes lead us to see significance in random events. When you're dealing with surveys of millions of stars across decades of observation, purely statistical fluctuations will occasionally produce apparent patterns that seem meaningful but are actually just coincidental. The researchers involved in the Vasco project have used sophisticated statistical methods to try to separate real signals from random noise, but the possibility remains that some of the vanishing stars are simply the inevitable result of looking at enormous amounts of data and finding the occasional unlikely event. Perhaps most importantly, there's the question of confirmation bias. The vanishing stars have captured attention precisely because they're mysterious and difficult to explain. This means that researchers might unconsciously be more inclined to catalogue borderline cases as genuine disappearances, while more readily dismissing observations that might suggest conventional explanations. The scientific process is designed to guard against these kinds of biases, but it's not perfect. The history of astronomy is littered with mysterious phenomena that seemed groundbreaking at the time, but eventually proved to have more mundane explanations. So, where does this leave us? Sitting here under our own patch of starlight, contemplating the possibility that the cosmos might be far stranger than we've imagined. The vanishing stars don't offer us easy answers. And maybe that's exactly the point. They remind us that for all our sophisticated instruments and elaborate theories, the universe still holds secrets that can humble our understanding with a simple, elegant mystery. What strikes me most about this whole phenomenon is how it challenges our basic assumptions about permanence and predictability in the cosmos. We build our understanding of the universe on the foundation that physical laws operate consistently across space and time. We assume that if we understand how stars work today, we can extrapolate that knowledge backward and forward across billions of years. The vanishing stars suggest that this assumption might be more fragile than we'd like to admit. But maybe that's not a weakness in our approach to understanding the cosmos. Maybe it's a feature. Science works best when it remains open to surprise, when it stays humble enough to let the universe teach us things we didn't expect to learn. The vanishing stars, whether they ultimately prove to be exotic astrophysics, observational artifacts, or something even stranger, are already serving that function. They're forcing us to question assumptions we didn't even realize we were making. There's something deeply human about our reaction to this mystery. We want explanations, whether they involve primordial black holes, stellar engineering by advanced civilizations, or glitches in the matrix of reality. But part of what makes these questions so compelling is that they touch on fundamental issues that have fascinated humans for as long as we've been looking up at the night sky. Are we alone in the universe? Is reality what it appears to be? What are the limits of human knowledge? These aren't just scientific questions, they're existential ones, the kind that connect our cosmic investigations to our deepest concerns about meaning and purpose and our place in the grand scheme of things. The ancient peoples who saw the stars as imperishable weren't wrong exactly. From their perspective, given the timescales of human experience, the stars really were eternal fixtures in the cosmic order. But we're now living in a moment when human observation spans long enough periods to catch the universe in the act of changing in ways we never expected. That's both humbling and inspiring. Humbling because it reminds us how much we still don't know about the cosmos we inhabit. Inspiring because it suggests that the universe still has the capacity to surprise us, to teach us things that will reshape our understanding of reality itself. Whether the vanishing stars turn out to be evidence of advanced alien civilizations harvesting stellar energy, exotic physical processes we've never encountered before, or simply the result of observational limitations we haven't fully acknowledged, they've already accomplished something important. They've reminded us that the cosmos is not a solved puzzle, but an ongoing conversation between human curiosity and the vast, mysterious reality that surrounds us. As we continue to build more sensitive instruments, catalog more stars, and extend our observations across longer timescales, we'll undoubtedly solve some mysteries while uncovering others. That's the nature of scientific inquiry. Each answer leads to new questions. Each discovery opens up new frontiers of ignorance. The missing stars are just the latest chapter in humanity's long conversation with the cosmos. They remind us that we're part of something much larger and more mysterious than our daily lives might suggest, participants in an unfolding story that stretches across billions of years and countless light years of space. And maybe, in the end, that sense of participation in something vast and mysterious is what makes these cosmic questions so compelling. We're not just observers of the universe, we're part of it, temporary arrangements of stellar matter that have somehow become capable of wonder and curiosity about our own cosmic context. The stars may be vanishing, but our questions remain, bright and persistent as starlight itself.